Another speaker who's confirmed for next year's forum is Stuart Russell, professor at Berkeley University. Stuart is joining us now via video conference from California. Welcome, Stuart. How are you?
Thank you, Bruno. It's great to be here. I'm sorry I can't be there in person.
Well, that's going to be for next year. Stuart, part of your work focuses on decision-making in AI, and recently you have emphasized the importance of steering away from developing AI for single objectives and taking into account the context in which AI is actually implemented and embedded. We have agreed that you will start with a short talk about the roadmap towards strong AI, how we go from here to there, what we need to pay attention to along the way, and then I'm going to come back and we'll have a few questions. So the floor is yours.
All right, thank you, Bruno. So first of all, let me say what strong AI means. Sometimes called artificial general intelligence or human-level artificial intelligence. So it means AI that can solve pretty much any task that you could give to any human or any group of humans to solve, and it would do at least as good a job, maybe better. And this means in the real world. It doesn't just mean, in virtual reality or on a chessboard. It means in the real world that we live in and function in. So first of all, let me say, it's not about to happen. It's not imminent. We're not going to wake up tomorrow morning and find that the world's been taken over. And second of all, you asked for a roadmap, but a roadmap suggests that once you have a roadmap, you simply go along the road and you get there. But if along the road there's a step that says, and then a miracle happens, right? We don't call that a roadmap, right? And I think really several conceptual breakthroughs have to happen between here and strong AI, and that's really important to understand. And unfortunately, unlike advances in hardware, memory size, processor speed, and data resources, unlike those, with breakthroughs, we can't predict when they're going to happen. So people always ask me, okay, when are we going to have human-level AI? And I say, I don't know. And also, it's very dangerous to make those predictions because they always turn out to be wrong. And just to give you an illustration of that, since this is CERN, if you look back at the history of nuclear physics, right, in the early years of the last century, we knew that nuclear energy existed. We had special relativity. We knew the mass defects between different atoms. We knew how much energy was stored and potentially could be released if we could make transmutations of atoms. But Rutherford, who was the leading nuclear physicist of that era, was absolutely adamant that it was impossible. And he gave a speech on the 11th of September, 1933, where he was asked that question, would it be possible maybe in 20, 30 years that we could ever release the energy of the atom? And he said, no, it's impossible. And then the next morning, Leo Szilard invented the neutron-induced nuclear chain reaction. So it went from completely impossible to basically solved in 16 hours. So that's what I mean by unpredictable. Fortunately, with AI, there's more than one breakthrough that we need. So, even if you think of this as a Poisson process, as the statisticians call it, it's still probably going to take a while. So what's missing? As I see it, there are roughly three major areas where we don't know how to make progress. The first one might seem very simple, systems that know things. And in fact, in the early days of AI, this was how systems were built, using the technology of mathematical logic. And we did have systems that knew things, that could reason with them, but they couldn't scale up and they couldn't handle the complexity and imprecision of the real world. And the reason why you want to know things is, first of all, so that you can do things like physics, right? It's hard to imagine building a radio telescope or a gravitational wave detector if you didn't know any physics at all, right? And we're not expecting that termites are going to start building radio telescopes anytime soon. So that's good. So we use knowledge to know things, but we also use knowledge to learn, right? We can understand what the gravitational wave detector is telling us. It allows us to learn something about the universe and about physics because we know a lot already. And this is probably the biggest difference between deep learning systems, which are all the rage these days, but we don't have any way of putting knowledge into them. So they're always addressing every problem from scratch, which means they require massive quantities of data to learn anything, far more than humans need to learn the same thing. The second big open problem is language, because language is how we acquire all of that knowledge. And so systems that could really understand language, that could actually extract the underlying knowledge content of books and journal papers and so on, that would be an incredibly powerful tool, because a system like that, unlike a human, a system like that would be able to read everything the human race has written and understand it and integrate all that information before lunch. The third big thing is the fact that we are able to operate successfully over long timescales. So let me expand a little bit what I mean by that. If you look at AlphaGo, right, which is the Go program that beat the world champion, AlphaGo seems to look ahead extremely well. It seems to operate over even longer timescales than humans can. It looks ahead 50, 60, 80 moves into the future. And humans don't have the short-term memory capacity to do that. Okay, so why couldn't you just take that algorithm and apply it to the real world? Well, what is a move in the real world? Well, if you're a robot or a human being, a move is sending an actuation signal to one of your muscles, right? And you can do that about once a millisecond. So if you look ahead 50 or 60 moves in the real world, that gets you less than 1/10 of a second into the future, which is completely useless, right? And we operate on timescales of minutes, hours, days, weeks, years. If you decide to do a PhD, that's about 1 trillion motor control actions. Right? Now, you're not planning them all out in detail, but nonetheless, we can make decisions on all of these different timescales and operate seamlessly at every timescale simultaneously. And also, well, how do we do that? We do that because we have all these different levels of abstraction. You know, you have the ability to type a single letter on your cell phone, but you can also think of it as, you know, typing a word. You can also think of it as, you know, text my son and ask him to bring some milk from the store, right? That's an action. You could have another action like do the shopping, right? Another action like, you know, get ready to go away for the weekend, and all the way up to, you know, multi-year actions. And this is what enables us to function successfully in the real world. And right now, we don't know how to get AI systems to operate that way. And in particular, we don't know how to get them to create all those levels of abstraction that allow us to function successfully. So those are the three big open questions, I would say, that we don't know how to solve. But any one of those would lead to massive advances in the practical capabilities of AI systems.
So you are on record saying that the biggest limitation is our ingenuity and then physics, right? Which one we're going to break through first, do you think?
So let me start with physics. Some people have argued that physics, the limitations of on computing that physics imposes would prevent us from achieving human-level AI. So I find this very, very unconvincing. So first of all, you know, our brains operate on physics, and they're, you know, clear existence proof that physics doesn't prevent human-level AI. Secondly, if you actually look at the physics, it seems that in a brain-sized object, you could do about 10 to the 35 more computation than the brain does. So we are 35 orders of magnitude away from hitting the real limits of physics. So in Max Tegmark's book, Life 3.0, he goes through this in some detail based on some calculations that other physicists have done. And so I don't think we have to worry that physics is going to prevent real artificial superintelligence. Ingenuity, I think, is the issue, right? There's these three, and maybe if we solve these three problems, there'll be more that we haven't thought of. They require someone brilliant to come along and have an insight like Leo Szilard did with nuclear physics to unlock those problems.
So let me pick up on a couple of other things you said. You used the word miracle, and you used it to describe kind of unpredictable events, right? Suddenly there is a leap and we didn't know where it comes from, or we didn't expect it, or we consider it impossible. But there is another kind of miracle that we see more and more when we talk about AI, and it is the notion of the black box, right? Do we even know why these machines work? The machine figures out that this is a cat and that's a dog, but we don't actually know why the machine gets to the result. I'm simplifying here, of course. But how far can we go keeping the logic of the black box central to the development?
In my view, it's just not a viable strategy. And there are several technical reasons for that I won't go into. But basically, intelligence is a complicated thing. The idea of the black box is that you put enough stuff into the black box, and then you have one organizing principle, which is to make the black box do a better job. And essentially, you jiggle what's inside the black box, and you keep jiggling and jiggling and jiggling and jiggling. Every time it does a better job, you jiggle it more in that direction. And that's it, right? So there's one principle, basically, of essentially randomly mutating what's inside the black box to try to get it to move in the right direction. And I just don't believe that one principle is enough to create human-level intelligence. And there are many other principles that we've already learned, actually over thousands of years. So going back to Aristotle, concepts of knowledge, elements of knowledge with precise mathematical semantics that can be combined according to fixed rules that are guaranteed to preserve logical truth. That concept is extremely important and is totally absent from the black box method. The idea that you can make decisions by projecting possible actions into the future and finding action sequences that lead to good outcomes, that idea is also thousands of years old, and yet it's completely absent from the black box approach. So it seems ridiculous to throw away miraculous conceptual breakthroughs that we've accumulated over thousands of years and just replace them all with this sort of one principle of jiggling the contents of the box until it gets better. And actually, we tried that. Back in the 1950s, there was this idea of program evolution, or what we more recently call genetic programming. The idea that you could take programs and do to them what evolution does to genomes, which is to do random mutations and then random combinations or pairs of genomes. So pairs of programs get mushed together to make new programs. So program evolution, people correctly said that in principle, if I keep doing this, I will create general purpose intelligent machines. But of course, in practice, that might take 10 to the 1 billion years. So, gazillions of times longer than the lifetime of the universe to ever produce anything useful. And people tried doing this with Fortran programs because that was the only programming language available. And it was a complete and utter failure. I think we've been amazingly lucky that the current black box methods are really surprisingly successful. But as you say, we don't know how they do it. And that's not a good basis for engineering progress.
Yeah. Algorithms can be both good and creepy, right? Depending on the context and depending on the application and where we put them to work. You're on the record saying that developing strong AI would be the biggest event in human history, but we need to make sure it's not the last event in human history. Can you elaborate?
Sure. So the biggest event in human history because human history, human civilization is the result of our intelligence. And this would be the first time that we have access to much, much more intelligence than we have inside our brains. So it's inevitable that it would change civilization forever. And quite possibly some of the other candidates for biggest event, like, developing faster than light travel or figuring out how to live forever, right? Those things are much more likely to happen if we have access to super intelligent AI. So the upside is really enormous. The downside, the reason why it might be the last event, is something that actually Alan Turing said. So Alan Turing is the founder of computer science and of AI as well in many ways. And he said that we should have to expect the machines to take control. That once he said, once the machine thinking method had started, it would not take long to outstrip our feeble powers. And it's just common sense, right? Intelligence is what gives us power over everything else. And now we're expecting to make something that's more intelligent than us, and yet we're going to have power over it
feel that we can
forever.
control it, exactly, yeah.
Right? How? So once you lose control to something that's much more intelligent than you don't get it back. So the question is, can we square this circle, so to speak, right? Can we produce something that's more powerful than us and yet have power over it forever? That's what I'm working on.
So many people would answer that by saying we need to build human values into the machines. How do we do that?
So building human values into the machines is a statement that sets off a lot of warning flags, especially these days. So whose values? How do you do it? What if you get it wrong? The problem that we have with AI right now, and the reason we would lose control, is that the standard model, so I'll use the phrase standard model because we use that in physics, right? The standard model of AI is to build optimizing machinery and then put in the objective for the machine to optimize, and off it goes. So you build a game playing program, you put in the objective of winning the game of Go, winning the game of chess, and off it goes. And that standard model is pretty pervasive. It's not just AI, it's control theory, it's statistics, it's economics, and it's a mistake. It's a mistake because if you put the wrong objective into a machine that's more intelligent than you, then basically you've set up a chess match between us and the machine where the stakes are control over the world. And we lose that.
Yep.
So the whole model is wrong, and we're already starting to see this, right? It didn't matter when the AI system was a toy and it was in the lab, and the worst thing it could do would be to beat you at chess, right? But as we move them into the real world, right? You look at the learning algorithms in social media; they are laying waste to our civilization. Why? Well, because they're defined with the wrong objective. And that objective leads the algorithms to manipulate humans in ways that have actually been deleterious to us, because the algorithm, that's not its objective. Its objective is to get you to click on things. It doesn't care what effect that has on civilization. We forgot to put civilization into the objective. So you get these really negative outcomes. And the solution is actually to get rid of the standard model altogether, to get rid of this idea that we have to specify the objective, because we can't. Right? And we've known this for thousands of years. Every time you get given 3 wishes by a genie, right? What's your third wish? Please undo the first 2 wishes because I screwed it up. Right? So we can't do it, and we know we can't do it. So we shouldn't base our engineering methodology on a false assumption that we can specify objectives correctly.
Yeah.
So what we should do is build machines that know that they don't know what the objective is. Right?
Stuart,
and that humility is what turns out to give us control.
Stuart, just to close, a question that is unrelated to this, but not completely. We live in strange times. You know, the year has been dominated by the COVID-19 pandemic all over the world. You are not here on this stage, but you are via video conference because of that.
Yep.
What role is AI playing in our fight against the virus? And do you think we are using it to its full extent at this point?
So that's a great question. Let me first say, AI is not a panacea. Many people ask, well, why doesn't AI just solve the pandemic if it's so clever? It's just not in that business, right? The solutions to the pandemic are social solutions and medical solutions. And AI, at best, you know, we don't have super intelligent AI. It cannot invent a cure for the virus. You know, at best, it could have provided us with a much better early warning system. So integrating data from many different sources to detect and characterize the very early stages of a potential pandemic. It can probably improve on the mathematical models that people are currently using, partly because it's able to integrate data at every level of abstraction. So we can, not using black box method, but actually using methods based on what we call probabilistic programming, where we can actually construct models that go all the way from the individual person moving and acting and infecting other people, all the way up to, you know, aggregate level data at the level of a state or a country, and can learn those models from collecting data at all levels of detail. So we could do a better job of pandemic modeling, and then that gives you the ability to do a better job of intervention and prediction. But all of that takes a lot of time.
Yep.
And arguably, yeah, we should have started 10 years ago, and it's a bit late now, and it's probably not going to have a real impact before the vaccine arrives.
Well, maybe we can start now to prevent the next one. Stuart, great having you with us. Thank you. I look forward to seeing you next year here on this stage. Thank you for taking the time. Enjoy the rest of the day.
Me too. Thanks very much, Bruno.
Thank you.
Bye-bye.